Now let's move on to confidence intervals and tests for categorical variables. Let's assume we have an example. We have exoplanet surveys, and in these surveys we have stellar systems, and they are flagged as either yes or no, depending on whether the respective system hosts at least an exoplanet. So now having an exoplanet is a yes or no category, and we want to do tests now on this categorical data. And we do this by converting the yes and no's for every sample data into a proportion of observations in this sample that were member of a category that we are interested in. So for example, from a list of 10 out of 20 systems with a planet, we compute the proportion of 50%. So this converts our categorical data to a data that consists of proportions P1 for sample 1, P2 for sample 2, and so on. And then we can do our statistics and our tests on the proportion data, which is now again a numerical data. So since we are now working on the sampling distribution, the central limit theorem for the proportion can be applied and states that the distribution of sample proportions is nearly normal, centered at the population proportion P, with a standard error that is inversely proportional to the sample size, and the standard error here is computed with P times 1 minus P square root. And the origin of this standard error formula here comes from the binomial distribution, because we're now interested in the category member of category of interest. So this is basically a Bernoulli experiment with a success or failure outcome, or a yes or no. So for every single system, this can be described with the binomial distribution. We recall that the binomial distribution depends on two parameters, n, which is the number of trials, and p, the success probability, and then b is the number of successes in a random sample. So we can compute the sample proportion p bar as the number of successes divided by the sample size. And we know that in the limit where the binomial distribution approaches the normal distribution, that the normal distribution has np as our mean value and square root of np times 1 minus p as standard deviation. So it follows that the proportion, which is b divided by n, is approximately distributed as a normal distribution multiplied with 1 over n. And we can simplify this, which then is a normal distribution where the n cancels out in the mean and also in the standard deviation, leading to these two population parameters. Let's look at an example. Let's say that 70% of all stars in the Milky Way are classified as member of a multiple system. Now, if you were to randomly select 200 stars from the sky, what is the probability that at least 90% of your stars in your sample will be part of a multi-star system? So, the population success probability here is, or the proportion is 0.7. Sample size is 200. We are looking at the probability to find a sample proportion that is larger than 0.9. Let's first check whether the conditions are met. We have an independent sample, yes, as stated in the text. And we are looking at approximately less than 10% of all stars, yes. Our binomial distribution should approach the normal distribution, and the criterion that we had was that the product of n times p and n times 1 minus p is sufficiently large, or these conditions are also met. Therefore, we can conclude that the sample proportion should be distributed according to a normal distribution with mean 0.7 and a standard deviation of 0.032. With this point estimate and with this standard error, we can now compute our test statistics. And it turns out that this is 6.7. We are now looking for the probability to find this test statistic, assuming a standard normal distribution, and this probability is very small. It's approximately 0. So this is how we construct the confidence interval for a proportion. We have the point estimate p bar from our sample plus minus the margin of error, so the critical C value, times the standard error on our sample proportion. And the standard error for the sample proportion is the square root of the sample proportion times 1 minus the sample proportion divided by n, and then taking the square root. And we can now look at how to adapt our framework for hypothesis testing when we do it on a single proportion. Again, we set up the hypotheses. H0 means that our population proportion is the null value. HA is then P is smaller, larger, or not equal the null value. We then calculate the point estimate, P bar, test the conditions. Then we draw the sampling distribution, compute the P value from the calculated test statistic, and then we make a decision. Now, be careful to distinguish between the sample proportion P bar and the population proportion P. When we are computing confidence interval, the confidence intervals are properties of our samples, properties of the data. Therefore, we use the sample proportion n times P bar, or for the standard error P bar times 1 minus P bar. When we do hypothesis tests, we assume a null value and we work under the assumption that this value is true, and therefore the standard error is computed with the population proportion that we assume in the null hypothesis. So be very clear about distinguishing between these two values. Another example. In a poll, they found that 60% of 1,983 randomly sampled American adults believe in evolution. Does this provide convincing evidence that the majority of Americans believe in evolution? Let's test. So, again, the null hypothesis makes the assumption there's no effect, so that we have a 50-50 case. So P is 0.5. Our observation, P bar, is 0.6. And the alternative hypothesis, P larger than 0.5, sample size 1,983. Conditions are met. Therefore, we can assume that P bar is distributed according to a normal distribution with a mean centered on the population proportion and the standard error computed as P times 1 minus P divided by the sample size and then taking the square root. This gives us a test statistic of 8.93 standard errors away from the population mean, and the p-value for that is 0. Based on that, we reject the null hypothesis and state the data provides convincing evidence that the majority of Americans believe in evolution. When we want to estimate the difference between two proportions, then we have to extend our framework similarly to what we did in the previous lecture. Now, the parameter of interest is the difference between two population proportions. Our point estimate is P, the difference between the P bar values. So this gives us the following confidence interval. The standard error computes from the squared summation of the standard errors of the individual proportions and then taken the square root. Our conditions are similar to the condition tests also from the previous lecture, where we test that for the individual proportions we approach the normal distribution with our binomial distribution. Let's look at an example. Let's say we have the following poll results, where respondents were asked whether any of their children have ever been the victim of bullying in school. Also, recorded in this survey was the gender of the respondent, so whether it was the father or the mother, and this is the distribution, and we find that when the male parent had been asked, 38% of them confirmed bullying of their children, while female respondents replied in 50% of all the cases. So we compare the two proportions now and test whether there is a significant difference. Again, the null hypothesis states there is no difference, so the proportion between male and female should be 0. The alternative not equal 0. And again, when we are dealing with confidence interval, we use the observed counts, and when we are using a hypothesis test, we use the expected counts and the expected proportions. Now, when we have two proportions, so when we are testing or when the null hypothesis states that the two population proportions should be equal to each other, then we still have to assume a certain numerical value to perform the hypothesis test. So what value should we take? And here we take the pooled proportion where we put all the respondents into a pool. So we count the number of successes in proportion 1 plus the number of successes in proportion 2 and divide it by the total of asked respondents. In this particular case, 34 out of 90 and 61 out of 122 were the two individual proportions. So here we pool it now. We get a pooled proportion of 0.448. So for the expected hypothesis test, we use the proportion P bar pooled to compute our test characteristics and to also compute the standard error. So, coming back to the example and assuming a 5% significance level, we conduct the test and evaluate if males and females are equally likely to answer yes to the question. After confirming that the conditions for the test are met, we find that the proportion of P male minus P bar female should be distributed according to a normal distribution with mean 0, because the null hypothesis states there is no difference, and the standard error of 0.45 times 0.55 divided by 90 plus the similarly computed standard error for the second proportion, giving us a standard error of 0.07. Our point estimate is minus 0.12, so we can compute the z-score again, this was the standard error, which is minus 1.74, and just ignore the square root of 1 here. That's because the framework that I used to compute the figure and the tables here was not originally built for the pooled case. So I assume a sample size of 1. So the z-score is minus 1.74, and the corresponding p-value is about 8%.